Hello, we again apologize for another unexpected power cut. Now the power is resumed and we'll be starting the session.
Yeah, okay. Yes, sir. Yes, sir. Yes, sir. Recording is on. This word password डालो. Hello. Hello. Am I audible? Hello. So we are restarting the session. Uh, so I'll quickly go to the Scratch directory. Just user one. CD day two examples. Then CD channel 395 LS. So these are the data points created last session. So we remove all the points by clean tutorial. So this command for foam clean tutorials deletes all the initial data points. So we check now the error files are there. We need to use this command rm job 14209 star and all the job files will remove and we have the default case folder. Now we activate the OpenFOAM environment. Where is that file? The OpenFOAM environment can be activated using this command and module load also we do it. So we go step by step. We copy that module load apps OpenFOAM 9.0/Intel and we paste it here and we activate the compiler first. Okay, so compiler has been activated. Now we source the OpenFOAM environment using this command source slash home slash apps slash openfoam slash 9.0 slash openfoam 9 etc bash rc. Okay, so environment is activated. Now we run block mesh. So block mesh command, and we see that block mesh is successful. Now we run simple foam. Oh, now we submit this bash file. I mean the slum file, that is terp.channel.sh. We submit it. It is submitted, and we check the status. It is running. Let it run. Now let us wait for 30 seconds till the data files are generated. So you can see the data files are being generated. So we prepared the directory for download. So day 2 examples. You go inside day 2 examples. This is channel 395. This is a older thing. ये कहाँ है? ये पुराना वाला है ना? Oh, ये home में है. So this is, as you can see, this is in home directory. So you have to यहाँ पे. So you have to change it to scratch. नहीं, फिर home में आ गया. आ गया ना? So you can see the data files are there, which has been generated. So let us download this data. So we select this channel 395 and we click on download the directory. So we are downloading this to desktop directory. It is downloading now. So you can see that channel 395 has been downloaded. So we now open ParaView. So we open the desktop file. We go to channel 395 folder. We open system file. We change to all files, the file type to all files, and then we click on control dictionary. Then in the open form reader, we select in ParaView and we select as OK. So this control dictionary file is available now. We click the apply button. We select the velocity field as the primary input that is displayed. So you can see that this is a 3D domain and how the flow structures are visible here. You have to adjust the view by clicking and dragging the geometry, and you play the animation. So you can see the flow is developing here. Okay. Now we'll try to create animation. So you click on file, you click on save animation. Here you will create a new animation. That animation was a previous one. So you create a new animation, anime 1, and you select your desired type of video, that is MP4 or AVI. I am preferring AVI and I'm clicking on OK. Now we have the image resolution. You can select or double it as per your requirements. As of now, I am choosing the default resolution. Quality is best in larger file 2, and frame rate is 10 or 15. So I am keeping it as 15 and I'm clicking on OK. So now the animation creation has started, and let us see after the animation progress, we'll be able to see the video. एनिमे 3 कहाँ सेव हुआ? Channel 395. Channel 395. So you can see the anime 1 file has been generated. We will visualize this. Open with media player, and you can see the turbulent flow animation. So that's it from my side. Now Snehal will continue.
Hello, I'm audible. Okay. So we'll start the dam break example. So go to that dam break interform folder, CD dam break interform. Then again go to the second dam break folder. Okay. So here previous files are there. So we want to delete that file, and for that we are going to use the command foam clean tutorials. Okay. Now you can see all folders are deleted. So already we have created the source for the OpenFOAM 9 version. So directly I'm going to run the commands. The first command is block mesh. So mesh is created. So whether to check mesh is correct or not, we can use the command check mesh. So here you can see mesh is okay. So now we need to create the fields. So we are running the command set fields. Okay. So fields are created and we are going to run the simulation. Okay. So you can see files are created, like results are created for different time steps. So we need to download these results into our system. So again, here I'm going to Dimebreak example. So we need to download this folder, Dimebreak. Download. I will download in desktop. Okay. So here you can see we get the files. So again, we open the ParaView. So go to File, click Open, then go to Desktop. This is a Dimebreak folder. Here we need to go to Folder System. You need to click All Files, All Supported Files, and here you can see the Control Dict file. So click Control Dict and press OK. Here you need to select the reader, which is OpenFOAM reader. So here you can see different variables: pressure, alpha water, which is volume fraction of water, and this is U. So initially, water column is like that, and after because of this destruction, how it will disperse, we'll see. So this is for very limited time steps. So I'm just going. See. So from control tick, you can change the time step. If you want to increase, you can change the time step. Now I will show how to save the animation. Go to File, Save Animation. So here, I'm not going to change frame rate because already time steps are very small. So I will keep it as it is. And image resolution will be same. So we are moving to next example. So in day 2 example folder, go to the column dense particle foam. Here also we are creating the mesh. I will try to run through as batch file. Let's see. Here we are running in serial. So number of tasks are 1 and we are just writing the name of the solver, that is dense particle foam. So we are going to submit job by using command sbatch space name of the script file. Job is submitted. Let's check whether it's working. So job is running. Okay, let's wait for some seconds. Yeah. Already there are files. Okay, now there are enough files. So I will cancel the job. Let's download this folder to our local system. Okay, meanwhile, I will open the Paraview. Select the open form reader. Okay.
It's okay. You just show the last it. Just the last it. Then okay, so I need to check. It's okay. Uh, Guys, there is a problem. We will update that solver, the test case again later, and we will post it on Teams. But now, some last information about this multiphase thing, what we are going to look for. Guys, can you help me? On the desktop, not this. So we'll share the PPT. You can really go through that. And what we are going is the last lecture, something about particles and their collisions, motion, and other things. So again, we are back to the same concept. Multi-phase systems, grid-based. What we want to really look is something about particle-based kind of techniques. And can we have particle and also mesh-based kind of techniques? Both are present. Here, what we are looking is something like combustion chambers, like jet engines and other things, what people try to look for. You will always have particles involved with that, and chemistry is happening. Maybe something like cyclone separators, flow will be there, particles will be there. Maybe something like landing aircraft engines, there will be a lot of dust which is interacting with that. It may even penetrate into engines. Maybe something like dusty storms are attacking some environmental kind of issues. This kind of things preferentially has lot of particles. That means volume fractions are so high interacting with the flow. That kind of systems, naturally one has to go track these particles, particle collisions, their momentum exchange, heat transport. Hello, am I audible? Yes. Okay, great. Such kind of scenarios, we require something Lagrangian entities also into the system, tracking these particles, their collisions. Great. So basically, in this kind of particle methods, you will have your own CFD, and also there will be moving particles. These particles moving by their F is equal to ma kind of thing. This flow is basically your Eulerian frame like Navier-Stokes equation, and they communicate with each other. Particles communicate with themselves, particles communicate with the flow, flow again communicate with the particles. That kind of thing, what happens at this Eulerian Lagrangian combined technique. So for example, in abstractions, there is something like a flow, some mesh, some geometry flow comes, goes. In that particles also present. These particles may be having different sizes. Small sizes, large sizes. Large comparable to mesh size, small way smaller than mesh size. So when you are going to do such kind of things, usually stress distribution on those particles supposed to be communicated on the flow field. For example, I am the person who is walking. I'm more like a particle. I'm pushing air by applying stresses on my body, and body itself is moving. When that happens, I need to really distribute this entire stress, apply it on the flow at every mesh level. As long as I'm very big size object, many mesh points are there in the flow, that momentum has to be distributed everywhere. So usually stresses are the key thing when objects are big. But instead of that, maybe hair strand much smaller compared to the mesh size. If I want to solve that kind of thing, mesh, maybe the hair strand, certain kind of object, I want to really move it here and there so that effective force act on the mesh. So something like stress distributed, effective force distributed on the mesh. These kind of strategies one has to do. So basically, when you have something like large size objects, stress has to be communicated. When it is small, you don't need to communicate stress because it takes a lot of communication, memory, and other thing. So effectively, you can distribute force on that. That means the smallest particle, what is pointed force on that? I will apply within that mesh carefully where that particle is present. If object is very big, throughout stress, I will calculate the stress information. I will act on that entire mesh. This is the way one has to carefully do. Maybe, for example, some abstract turbulence flow field is there, some zoom up view of maybe combustion chamber, some black dots are there. Those are the particles. The turbulence interact with particles. And if I want to simulate that kind of thing, first one has to decide what kind of turbulence you are trying to do, what kind of length scales involved in that. The length scales involved in the problem way larger than tiny particles. You purely go with Eulerian flow field with Lagrangian particles. No, there are some small structures are also available within that comparable to your particles. What you do is wherever particles comparable to that, you go apply this stress distribution. So that kind of to and fro kind of things happens on the systems. So again, repeating, particles are comparable to local turbulence scales. You are going to resolve them having very fine mesh. That means a lot of computation one has to do around each of those particles. Wherever particles are way smaller than mesh kind of things or flow scales, you use reduced order kind of equation. Something like F is equal to ma kind of equation, m velocity dot acceleration, some fluid forces acting on the system, some kind of acceleration terms, some drag kind of terms, some buoyancy, some history, Bassett kind of forces. Something on that particle you will solve is much easier compared to resolving increasing mesh resolution. So this is more like ordinary differential equation for each particle. That is partial differential equations for each particle. So which flow of the domain you will have, there will be control kind of things. You carefully pick, resolve that. Where you will really check resolution is not required, you will tweak that. That way, some of these solvers work in some sense. Especially where you use, if it is completely dilute kind of flow. If this size is way small, you straight away employ Lagrangian kind of technique. Their size comparable. You go with stress distribution, mesh resolution, and other things. Maybe completely contact kind of things are happening. You need to really resolve the meshes because what is happening in between them, one would like to really have. Then naturally you resolve it and do that. When highly colliding and so on, you need to really resolve the meshes. It's okay kind of thing. Based on which kind of dynamics you are looking, you employ Lagrangian. So based on that, people try to really plot what is their size of the particles, volume fractions I am using, what kind of characteristic flow scales involved in that problem. Based on that, people really realize, do I need to fully resolve? Do I need to one-way couple? That means particles will be advected by the flow, or particles can have back, particles can rotate and affect the flow. This kind of things people usually go. Though the numbers are not important, that kind of plots are available. Based on that, one will be in a position to really sense which regime they are in, what is the correct method one should really use. That is the place where, in some sense, a compromise happens and OpenFOAM has one particular solver, particle in cell method. We'll shortly see what is that. There is a tool available and one can really use. For example, in abstractions, the flow mesh is this. So you will solve flow equations only on that mesh. You don't really resolve around them. But this particle in cell methods, what they do is, wherever they cluster that kind of zone, they will identify in some sense. Oh, the volume fraction is a lot. I don't want to resolve, but I will introduce some kind of probabilistic transport equation. I will solve the probabilistic transport equation in terms of velocity, size kind of thing. Identifying cluster. Oh, they are very large. So instead of resolving, I will use probabilistic description to really sense what kind of velocities around that really created. And that summed value or coupled value, you bring it, apply it on the flow field. So a bunch of particles having different velocities, different sizes kind of thing, locally based on their volume fractions, based on the velocities, you develop one more equation, kinetic transport kind of probabilistic equation. Solve that. Once you solve that, one will be in a position to really sense probabilistically that particle will have this velocity, this will be having other velocity, and other one will be having other velocity. We'll see one more abstract. So think of in this way. You have original field, a lot of particles are happening. In some sense, based on the clusters, project it, all these particles, I'm going to solve it like one particle. So in this mesh, 1, 2, 3, 4, 5, 6 particles are there. You don't solve for all that 6 at that instant. You treat them like single particle, try to solve that. Maybe you want to resolve the meshes, resolve around them. Once you have that, again you go furthermore like a kinetic transport equation, this entire description for this 6. So that you add back it, try to get the information of that 6. That kind of techniques, if people use it, they call this multi-phase particle in cell methods. Multi-phase particle in cell method, MPPIC kind of schemes. So you treat bunch, solve the transport equation, resolve anything, whatever you want to do that. Even Lagrangian. Then use kinetic transport equation. Again, go back, try to identify where these particles are moving and so on. In that sense, even millions, billions kind of particles, you can reduce to mesh level, get the information, again explore, try to get local level. Otherwise, maybe solving billion Lagrangian identities is huge task. Maybe resolving meshes, trying to get particle flow field around that is very difficult. So a kind of compromise, what one can really do. Typically combustion and soot kind of things, aerosols, people go with this kind of multi-particle in methods. So the transport equation, what I was talking about is this one. It looks like advective, but kinetic transport kind of equation. There are certain terms. Those integral values, the bunch gives you particle volume fraction, particle density, particle velocity locally. Once you have that, that gives you coupled kind of terms. You solve that, you plug it. Finally, solve, add back the forces, get the information. Is that kind of strategy what happens on summary? So especially the solver dense particle form is MPPIC kind of solver. It's a transition solver, coupled transport of single kinematic particle cloud, including the effect of volume fraction. So that bunching operation, what it does. You don't want that coupled kind of thing. There is another solver, uncoupled kinematic partial form. You just want to add back the things like aerosols. Reactions are also there. There is something like reacting partial film kind of form, so that droplets, sprays, and other kind of things are happening. People use that. Spray foam, another variant kind of thing with compressible effects. So whole point is some Newton's equation of motion with effective forces one has to solve. You will solve for that particle velocity, then particle velocity integrated to get position. So that particle location one will be in a position to sense. And these effective forces, people require empirical models like drag, gravity, particles, and other, because you don't solve the complete particle around them. So for that purpose, they usually go with maybe drag force acting on the particle, depends on what is the drag coefficient, what kind of particle size, what is the relative velocity between particle flow, and the drag coefficient based on certain empirical things. If particle is moving with this particular velocity, Reynolds number must be this thing. So that use drag coefficient will be something like 24 by RD with corrections. Maybe if it is very high flows, use other kind of drag coefficients. Any kind of empiricism is there. But unless that kind of things are there, one cannot integrate that particle solver. And people plot, try to sense that this is the value what I am using, finally getting this integration. Similarly, gravity forces on the particles to be included. One will be in a position to include what is the mass, what is the gravity, and so on. Maybe something like additional forces required because of pressure gradients and so on. There are some terms which one has to be included. And including all these things, people try to sense whether I really require all those contributions or some of the things I can really chuck out. That people do it based on some number named Stokes parameter or Stokes number. How quickly an object accustomed to the flow. If it is very quickly accustomed to the flow, is basically act like a tracer. So your Stokes numbers will be very small. Skip some of the terms. No particle has its inertia. It can't so easily take a turn. Even flow is trying to take so that it influences the flow. Then Stokes numbers are large. You include certain terms. That is the way people tweak it. When particles are quite close to each other, they have inertia. They can hit each other. They should bounce. They should deform. Maybe they should rotate. They should contribute certain kind of force and stress distribution. For that, again, certain low dimensional models like spring dash, uh, dashpot, and mass kind of models they will have. And based on that, how much energy is supposed to lose, how much reflection happens, one will be in a position to take care of certain contact forces. Hertzian kind of description and other things are there. So these are the modules to take care of additional impact of these particles. And all these things in some sense available at this dense particle form. If you are looking at that, compared to your interform or other icoform kind of solvers, you will always have additional fields in the creates fields.h, something like kinematic cloud. And that is the place the densities, velocities, viscosity, and other parameters in some sense clubbed. And if you are looking how it works, you will always have some pressure velocity coupling like pimple. There will be some U equation, pressure. When you are looking at that U equation is for the flow. Additional force terms comes at that U equation because of these particles. Something like your U equation, if you are looking d by dt U, divergence terms, turbulence terms, and so on, additional terms like particle force terms come into picture. So you will force that flow. And there will be options also, option files if you are seeing when you are compiling the things and solve an additional thing. There always be additional Lagrangian path packages come into picture, libraries. So if you look at that open form 9, there are Lagrangian dense particle form, different applications are there. What you have to do is go to that particular thing, run it like whatever you are doing. Then injection, cyclone, these particles will be available. You will be in a position to visualize these kind of things. That is the way this particular solver works. Okay. And that's from our side. But essentially, we skipped one particular topic very quickly. In 5 minutes, we can go. We try to look at two extreme, something like interfaces, no interfaces, but particles, phases supposed to present. In between that, there is something like multiphase Euler form. So instead of particle base or dispersed kind of things, instead of volume thing, there is one more Euler multiphase forms are there. You have very complex kind of thing. Turbulent motions are required, but this resolution and other things are a bit difficult for you because you do not have that kind of computational capabilities. So this Euler kind of techniques helpful in that case. For that, you write two separate equations, your Navier-Stokes equation. Some couple terms comes because of kinetic theory. You include those things and simulate it. It is the oldest and traditional fashion of understanding multiphase flows. So estimating volume fractions, momentum equations, and so on will be there. Basically, you will have the same simple algorithm. Instead of solving just one set of equations clubbed with another set of equations, do it parallelly. So go through the PPT, we will update you. Basically, you solve transport equations, club them. That requires additional closure terms. You model those closure terms via certain kinetic theories and go ahead, solve even energy equation based on which result, which parameters to be tweaked. Some empiricism always be there in terms of those closure terms. When you are looking at the code, basically you need to look at multi-phase Euler form, the present version. The oldest version is two-phase Euler form, the C file. There always be something like scalar fields, d by dt terms, divergence terms in terms of that. In addition to one equation, there will be one more equation. Two phases supposed to be there. U equations clubbed with them. After that, energy equation comes. After that, pressure equation comes. Once you are done, you go back again, solve alpha first equation, alpha 2 equation, come back U equations, C equations, P equations. That is the way structure really works. So if you are looking at the code for alpha, you definitely require this transport equation that is solved via algorithm named mules. So basically alpha equation to be solved, you will always have certain additional terms, and those terms, how you are modeling, how you are clubbing, one will be in a position to solve it. So open that mules templates.c kind of algorithm. You will sense there is some transport equation, some divergence term, some additional closure terms one will solve. Oh, it's very small. Look at it, and once you solve that velocities to be approximated, you use those velocities information, go ahead, solve your original momentum equations, club those stress terms or perhaps these alpha terms into your momentum equation via additional force terms, the SP kind of terms. Then solve pressure equation. There always be terms coming from momentum equation to solve pressure. Once you solve that, your conservation happens. You go back and do the same step repeatedly. That's the way this multi-phase Euler form really works. So the example is basically industrial reactors like bubble columns, fluidized beds, and other one will solve. So we will provide you test case. Same thing we will, after this workshop is done, we will provide you these PPTs and also test cases. Steps also we will record it. You just need to copycat, do that even on your local machine. With that, you will be in a position to really get acclimatized with multi-phase situations, turbulent multi-phase kind of situation. Okay. Thank you, everyone. With this, we would like to really close. And it's our pleasure. If you have any doubts, the Teams account will be there. You can always post and we will get back to you. Okay. All the best. Bye. Thank you all, even online participant. Bye.